go live link and see if that's looking a little bit more positive for us. Got it. Oh, 11 p.m. over there. We've got some people. Fantastic. Just check we're up and running. We are live streaming. What do you got? Webinar is now live streaming. Let's refresh that page, make sure everyone can join us. And hello to anyone who is joining us over on YouTube. Hello. Fantastic. Sorry that took me a little bit longer than usual to get set up. You'd think I'd be slightly better at it by this point, wouldn't you? Let me share my screen and get us started today. You should now be able to see our lovely Department of Physics, along with a selection of, we think, delightful views of equations, particle accelerators, and solar cells. So hello everyone, welcome to the 8th webinar of the Preparing for the PAT course 2024. We are set up on YouTube, so hello to those of you who are on YouTube, and hello to those of you who are on Zoom and have already said hello. My name is Kat, my pronouns are she, her, and I'm the Access Officer for the Department of Physics. That means I run most of our programs for secondary school students, including all of our stuff to support people like you interested in applying physics here at Oxford. Today's session is being recorded and it will be made available to you tomorrow. Quick reminder of the housekeeping rules for those of you joining us on Zoom. You are able to use the Q&A for any questions that you'd like to be addressed. I'll let you know when it's switched on and ready. And you can also access the chat to share thoughts, but please keep it polite and kind. Do not share any personal details or information, and don't use it for any questions that you want us to answer. Pop those in the Q&A, otherwise they'll get lost in the chat and we won't see them. If at any point you are feeling unsafe or you're concerned about anyone, you can contact our safeguarding lead on safeguarding@physics.ox.ac.uk. For now, let's get started. I'm going to do a very quick introduction. Those of you who have been with us a few times will have seen this introduction, in which case this is your chance to go and get a cup of tea. I'll give you a shout when it's time to come back and join us. However, those of you who this is new to, let's do the basics. So I will not take questions, just so you know, by the way, I'm not going to answer questions in this point. I'll come back to those later. First things first, the PAT is the physics admissions test at Oxford University. It must be sat by all candidates for physics, physics and philosophy, engineering, and materials science. Your result on the PAT forms part of the information which admissions tutors use to decide who to shortlist for interview. To sit the PAT, you must register yourself as a candidate. Your school will not arrange this for you. The PAT this year will be on screen and multiple choice. There will be roughly 40 questions with a total of 100 marks. We've worked really hard to make sure that we can gain as much information as possible from this format, so the answers are not just 1 mark or 0. The online test includes a built-in calculator, which looks exactly like a regular calculator and works in just the same way. You will do your exam working in an erasable booklet, which cannot be removed from the exam centre. Other important things to let you know are that the PAT syllabus is also online, and it is your responsibility to ensure that you have covered it, either by self-study or through your studies so far. That is the very basics of the PAT. The PAT course, the Preparing for the PAT course, which you are in a webinar for, is a course which we run on behalf of all subjects who require the PAT. It's aimed solely at students who are taking the PAT this October. If you're not taking the PAT this year, we've got lots of courses which we run for Year 12s, which lead up to this course. And I recommend that you take those first and then join us on Preparing for the PAT 2025. I'll see you next year. Preparing for the PAT course is a set of 8 webinars along with problem sets and summer assignments, and we hope to provide you with all the information that you need to take the PAT, help you prepare for the PAT, and be confident going into interviews if you are shortlisted. The timetable on the screen at the moment is part of every PAT email. It's always highlighted, and we're on the final session at the moment. It's our final webinar. We're highlighted in yellow, and you can see that today we're going to extend our session up to 8:30 for any remaining questions, but the bulk of our session is going to be 2 of our undergraduates leading you through the solutions to problem set 4. If you are joining us for the first time, you are going to want to head over to our website where we have all of the course materials along with recordings and everything else that have been part of the course up to this point. Right at the top, we've got our Introduction to Physics Problem Solving, How to Be a Physicist, which we looked at very much first week and last week. So you had our circular problem solving. And then underneath are all the links that you might need. So for example, under webinar 1, there's the problems that were used, the recording, and the links to the problems we asked you to solve for webinar 2. In terms of finding information, because we always get asked for this, all of the information that both you and your school need can be found at the page which is there. It's in every email that I send, so you'll find it tomorrow morning when I share the recording. It's the most up-to-date page. It's the one to check for any information that you need. It has links to the syllabus, the practice paper, registration links, and it has an excellent FAQ page, which is really useful. Quick key facts for you before we move on for the rest of the day. All tests this year will be sat at Pearson test centres. These venues are in almost every country around the world. When you register, you're able to select a centre which is most convenient for you. For some people, this is going to involve some travel, hopefully not too much. This arrangement is different to previous years, but it's the same as the setup for tests like the LNAT, the BMAT, and the Cambridge admissions tests. So you'll get more familiar with these, and Pearson are the experts at running this kind of test. Registration for the PAT opened on the 15th of August and closes at the end of this week. It closes on the 4th of October. You must register by then. We cannot accept late registrations for any reason. So if you've not registered and you're watching this webinar, after we finish, get registered. When you register, you can select a test centre, and you can also apply for access arrangements at the same time. So if you're in the position where you haven't registered yet, you're going to need to have all of your documents ready and get registered by this Friday. The PAT is being held on the 28th of October, which is a Monday. And I mentioned earlier, we've got this new test format, the on-screen multiple choice. It is not as big a change as it seems. The questions are going to feel really similar. The syllabus is unchanged. However, we don't want anyone to feel anxious, and so you can access a trial version of the test along with the calculator, which is on screen, and the solutions. Those are all available now. That is my quick PAT introduction and update. I'm going to stop sharing my screen now, so I should be back in the middle of your page. And I am going to hand straight over to our lovely undergraduates who will be taking you through the solutions to problem set 4. I will share these problem set, link to the problem set in the chat right now. So let me copy and paste that. So anyone who was unable to find the problem set or hasn't had a chance, we're popping that up now. Oh, I've accidentally only sent that to Aggie and Roxanne, who are already here. They know the problems. They're about to take you through the solutions. Let's send them to everybody else. And Aggie, I will hand over to you. I will man the chat and the Q&A. So if there's anything that needs to be sent over, I will make sure you catch them. Could we please not use the chat for questions that you need answering? So I can see I've got a question about registering for the PAT. Don't pop it on the chat. I put those in the Q&A so that I can answer them for you. Without further ado, Aggie, over to you.
Nice. So let me just share my iPad screen so everyone can see that. Um, there
I'll
we
keep my
go.
microphone turned off until we're all shared so we can check that we're seeing everything.
This is Yeah, okay, good. So
Yeah.
that should be there. And just because of timing and basically I'll kind of go through the question fairly not too quick, but we're kind of slow enough such that everyone understands, but fast enough such that I don't take too much time. And then basically because I can't really see the Q&A and answer the question at the same time, if anyone has any particular questions, I will answer them in the chat, in the Q&A section of the chat, while Roxanne will present number two. Right, so let's start with question one. This is a diagram which I've prepared earlier. So let's kind of read the question. So we have a fishbowl of height 4r over 3 is formed by removing the top third of a sphere of radius r. The fishbowl is fixed in sand so that its rim is parallel with the ground. A small bubble of mass m rests at the bottom of the fishbowl. Assuming all surfaces are frictionless and ignoring air resistance, find the maximum initial velocity that could be given to the marble for it to land back in the fishbowl. So this is quite a loaded question. So before we do anything, let's try and break it down and kind of introduce some variables. So clearly, I'm sure that you've seen a fishbowl before. When we have the marble here, if we give it some initial velocity, let's call that initial velocity v naught. If the velocity is small enough, essentially what's going to happen is this marble is going to just kind of, go back down, go up, and then slide back down. But obviously, if the velocity is much, like very, very large, the marble will eventually, shoot out of the bowl, right? And if our velocity is too large, it's gonna, it's gonna shoot out the ball and it's gonna fall out of the bowl. But essentially, what we want is to find the velocity. We want to find what was the question? We want to find the maximum velocity with which we can kick the marble such that it does not leave the fishbowl. Right. So again, when you see our maximum or minimum, you might be thinking that we have to be some inequality involved or some differentiation. Oh, sorry, not differentiation. Yeah, differentiation. But a very much easier way to do this question is to consider, well, what is this limiting case going to look like? And clearly the limiting case is going to look like the marble is going to travel down this side of this side of the bolt, and then it's going to go down, and then it would hit the bolt right here. So that's kind of the situation that we're going to be studying. So let's just kind of add some labels. So at the point where the marble is just about to leave the ball, it's going to have velocity v1. Then we're going to call this distance that it's going to end up traveling. We're going to call it s, and then an subscript x because it's traveling in the x direction. Actually, let's just call this x just because to make matters a bit easier. So we're just going to call this x. And then finally, let's just kind of add some random lines just so we know kind of how the angles are going to look. So we have we have theta again, and yeah, that's basically everything that we need to solve this problem. So the minute that the marble leaves the fishbowl, right at this very point, it's going to just have the usual motion under gravity. Just the usual Suvat equations. And that is all the physics that we're going to need at this question. So let's kind of find as much information out as we can, and then we'll kind of see what to do with this information, right? So let's find, well, we know that the radius of a circle is r, so we know that this distance is equal to r. And then hence, this side of the triangle right here, because the height is 4r over 3, has to be r over 3, like so. So now, just using Pythagoras, because of the way that I sketch the triangles, I can find the distance x. So let me just kind of write it down. I have r squared is equal to x over 2 squared plus r over 3 squared. And to solve this equation, you simply get that x is equal to 4 root 2 over 3r. Good. Okay, so we've got the horizontal distance that this kind of marble is going to travel in this limiting case, right? I've already established that this is going to be the limiting case, so I don't need to care about any inequalities or anything like that. Right, so we can also find theta. So just kind of using trigonometry, we can see that sine theta is equal to x over 2. Just kind of make a little bit of a more clear drawing of the triangle here so it's more obvious to everyone. So this is r over 3, this is r, this is theta, this is x over 2. So usual trigonometry, and we get that sine theta is equal to x over 2 times 1 over r, which plugging in our equation from above is equal to 2 root 2 over 3. And the same thing with cos theta. So cos theta is equal to r over 3 times 1 over r, which is equal to 1 over 3. So now we've kind of got all the information that we need. We can look at the projectile part of the motion. So again, we'll solve it in the usual way that we look at these Suvat equations. So let's consider the horizontal motion. Not the horizontal, the vertical motion. So vertical motion. And let's write down all the information that we have. So we've got a marble that starts at this point. Let me just maybe copy and paste the diagram so it follows me around. That way, it's going to make it a bit easier for everyone to see what's going on. So I'm basically going to work out the Suvat motion for a marble that leaves the fishbowl at this particular at this particular point. And I'm going to use all the information that I've worked out above. So vertical motion, let's just kind of write our displacement, initial velocity, the final velocity, the acceleration, and the time, right? So the vertical displacement. Okay, well, clearly it's going to go from the point of the fishbowl, and then we want it to go back into the fishbowl, right? That's the limited case that we are studying. So in that case, the vertical displacement is going to be 0. The initial velocity, well, we're resolving our velocity, just the blue v1 into vertical components. We see that the initial velocity is equal to v1 sine theta. We don't know what the final velocity is going to be. We know that the acceleration is minus g, and we're just going to call the time t. Again, just a kind of an aside, I'm defining up to be positive and down to be negative. Good, so that's our vertical motion. So we can kind of look at our Suvat equation, see which one has all these variables. And the one that has it is S is equal to U T plus a half A T squared. I'm going to plug in my variables into this equation, and I get that 0 is equal to V1 sine theta t minus G over 2t squared. And clearly, I'm not interested in the t is equal to 0 solution because that's just the beginning of my motion. I find that t is equal to 2v1 sine theta over g. Good, so I'm just going to call this equation 1. And now let's have a look at the horizontal motion. And I think at this point it's an obvious fact that gravity only acts vertically, so we have no other forces acting horizontally. And for those of you who might be wondering, well, what about the normal reaction force? Well, the marble just about leaves the marble leaves the bowl at this point, which means the natural reaction force is 0. And if you were present in the circular motion session a few weeks back, you would kind of already know that. But if you're not sure, then I can answer that in the Q&A after. So for our horizontal motion, we just have that the time is equal to the distance traveled, which in this case is x. Speed is equal to this. No, the time is equal. Yeah, the time is equal to the distance over the horizontal speed, which in this case is going to be v1 cos theta. Again, just sort of resolving the velocity into vertical and horizontal components. So that's going to be our second equation. And remember that for x, we actually know what x is. X is equal to this. So this is just 4 root 2 over 3 r times 1 over v1 cos theta, like so. Good. So I have 2 equations for my time here. I have equation 1 and equation 2. So if I'm correct with everything that I've done, I think I might have messed up somewhere. No, this is the time. No, okay, good. Fantastic. Great. So this is my equation 1 and equation 2. So I'm going to now equate them to each other because I want to find V1, right? Again, I'm just kind of trying to get as much information as I can, given what the question looks like, right? Clearly, I'm not going to be using anything like, I don't know, wave motion or anything. I know that it's a marble traveling through gravity, so it's going to be some form of Suvat equations. So let's equate equation 1 and 2. So we both have t on the same side. And again, for the purpose of time, I would just simply show you the solution that once you equate equation 1 and 2 and subs in the values for cos theta and sine theta that we found before, you get that v1 squared is equal to 3gr. But of course, we don't want the initial velocity. We don't want v1 squared. We want to find v0 squared, right? As per diagram here. Well, to find that, we can use the other tool in our toolkit because we've already used the Suvat equations. We can use the conservation of energy. So let's call this point A and let's call this point B. Actually, let me maybe copy and paste the diagram again. So we have points B and point A, and let's equate the energy at these 2 points. So at point A, my energy is just going to be equal to a half mv0 squared. And at point B, I'm going to have my kinetic energy as per usual. And then I also have my gravitational energy, which is going to be mg times the height, which is 4r/3. So I equate these two energies due to conservation of energy. So I get a half mv0 squared is equal to a half mv1 squared plus mg 4r/3. And then all you have to do is substitute equation 3 into this equation 4. So 3 goes into 4. And then you will get an equation for V0 squared. And again, for the purpose of time, I'm just going to write it down that V0 is equal to the square root of 17gr/3. So to conclude, I basically, instead of bothering with inequalities, I considered what the limiting case would look like. And then I realized that the limiting case is going to be a very simple, well, not very simple, this is not a very simple question. It's going to be an application of Suvad equations, which then I solved the usual way using the information that the question gave me. So that's kind of how you do question 1. And I'll pass on to Roxanne to do the next question.
Hello, so I'm going to do question 2. Okay, let me share my screen.
Fantastic. As well, Roxanne is getting set up. I'll remind you, if you have any questions about question 1, Aggie has now switched over and is manning the Q&A. So she will answer your questions. I know there were a couple about alternate methods of solution. Roxanne, I can see your screen perfectly. Are you ready to go?
Yeah, I'm ready.
Fantastic. I'll switch myself back off. So questions to Aggie and Roxanne in the Q&A.
Yeah, so I assume you have read the question. So just be reminded that you may need to turn this into weight. And also for this ice ring, that means there's no friction between the trusses and the surface. Okay, so to do this question, you have to construct a force diagram of the structure, two trusses. And so first there's a weight with of weight 500 Newton, and then there's also two weights, the weight of the trusses. I labeled them as W, and this is 1.5 meter because it's in the middle of the truss. And also there's like normal reaction here and also normal reaction here, and also there's a tension here, a tension here. So by symmetry, like they are the same. And so because this system is in equilibrium, so if we consider the vertical forces, so you can see that 500 plus 2W equals 2R. So 500 is the downward force, and 2W is the downward forces, and they equals 2R. So upward forces equals downward forces. And so you get the expression that R is equal to 250 plus W. And so after considering the translational forces, we can think about the rotational equilibrium. So because the structure doesn't rotate, so if we take moment about like any point, the moment, like the clockwise moment should be equal to the anti-clockwise moment, I mean like the magnitude of them. And so if we try to take moment at, let's say, this point, I name it as point A, and if we only consider truss, so let's consider well, it's the same to consider like the left or the right one, but let's say I consider the right one. And so let's take moment about A. And so if I label this as theta, and then the anti-clockwise moment will be W cos theta times the length, which is 1.5, because here is 1.5, right? And then plus T sine theta times 2.5, because here here this is 0.5, so this length is 2.5. And this is the anti-clockwise moment. So regarding the angle, because the formula for moment is R F sine theta, right? Where theta is the angle between them. And so if I label this as theta, and then you can do some like mental calculation, and you will know that this should be cosine and this should be sine. And then they are equal to like the moment here, so it's R cos theta times 3. And so if you rearrange this, then t sine theta will be 6R cos theta minus 3W cos theta over 5. Yeah. So let me repeat it again. So if we take moment about A, then this is the clockwise moment, and then this is the anti-clockwise moment. Yeah, just to make it clear. And then we have this equation and also this equation. And if we substitute R equals 250 plus W into, let's say I label this as equation one. And after some simplification, you'll get T equals 1500 plus 3W over 5 times cos theta over sine theta. And so now we have the value of we have the value of W, and now we are trying to find theta because the answer should be a numerical value. And if we consider the system again, the system is the same one. So if we consider like, let's say this triangle, and so we know that here should be 2.5 meter, and then here is 1.5 meter because the rope is 3 meter long. And so by Pythagoras theorem, we know that here is 2 meter long. And then to find theta, because at first I defined theta to be this angle, and we have to find, actually we don't have to find theta, we only have to find 1 over tangent theta, because this is equal to this, right? And then we can substitute the value into this equation to get a numerical answer. And so T equals 1500 plus 3W over 5 times 1 over tangent theta. And 1 over tangent theta is actually 1.5 over 2. And so by using the fact that W equals 400 Newton, so this is the numerical answer, not the final one. Yeah, so after some like calculation, you will know that the final answer is 405 Newton. So the tension is 405 Newton. And yeah, and that's what you have to find for this question. Yeah.
Lovely. Thank you so much. I think you've got a couple of questions about contact forces between the trusses. So if you don't mind popping over and answering those. And Aggie, I believe it is over to you for question 3. And I think, have you also posted about a mistaken question 1?
Yeah, so I
leave
just want to kind of address. I don't know. I think I just said that the natural reaction force at V1 is 0 because I'm used to it. But when I obviously I just kind of used to it being the case. But it's not actually the case. And then I realized when people started asking me if you can do it via circular motion, and you can, because you can do it by circular motion by first resolving the forces parallel to the fishbowl at the point at which it leaves. And then they have to be equal because there's no resultant force in circular motion along the surface. And then when you resolve perpendicular to the surface and use your circular motion equation, then you can find V1 that way. I'm quite sure. I haven't worked through it myself, just because I didn't get a chance to do it now, but I think that should work. And yeah, just kind of ignore that comment about the reaction force. I was just, yeah, I said the wrong thing, I guess.
Not a problem, at least. We all do it. We're problem solving live. So we're taking you through
Yes.
the process. Thank you so much for that. Let's get over to question 3.
Good. Anyway, so yes, question 3. I'll try to not make mistakes this time. But yeah, I mean, it's good, don't trust everything that I say. I can also make mistakes, right?
No, absolutely.
Good.
I'll also, just before you get started, because today's the final webinar, I'll be posting full solutions to all the problems that we've done tomorrow morning. So anyone who needs those will be able to both watch these again so they can see you doing it live and have a look through the written solutions too.
Good. Right. So the maximum range question. The first part of the question, because there are 3 parts, says, show that the maximum range of a cannon on flat ground is achieved by launching at an angle above the horizontal of theta is equal to 45 degrees. Right. So let's kind of draw this out, exactly what this problem looks like. So we have a cannon and we're going to launch it at theta, and we don't know what theta is, right? And the cannon is going to reach, is just going to simply kind of travel a distance r, right? And then we want, the maximum value of r. So how do we find it? Well, let's kind of, use our Suvat equations and describe the motion. But let's use a little trick. Because of symmetry here, you can see that the motion on the left-hand side is exactly the same as the motion on the right-hand side, because this is just a parabola, right? With the minimum here. So let's just kind of consider this half of the motion, just to make our life easier. And yeah, because we know, basically because, and I'll explain why, because for Suvat equations, we need information, right? And the easiest way to get that information is kind of knowing facts which hold in all in all Suvat equations. For example, we know that at the top, at the maximum height, the vertical velocity is going to be equal to 0. Sorry, that doesn't mean vertical, right? Because it's just as it's about to fall down, right? So let's kind of quickly consider how the time that it takes for it to get to this maximum point, right? So let me kind of explain my thought process again. So I want to find this range, right? But obviously, like, I have this variable v that I have here, and like the point is I can introduce many, many variables to this problem, but there's no point of introducing that many variables to this problem, because I can just kind of use symmetry and simplify my my solutions slightly easier, right? Sorry, I'm going to call this u just to make it easier. Good. Okay, so let's first define the time that it's going to take for a projectile to go from this point all the way to the top, right? So let's write down our information. So again, vertically, let me just kind of write that down. We're going to have S, U, V, A, and T. Here we're going to have U sine theta. Then we're going to have the displacement, which in this case is going to be equal to, well, let's just call this, well, actually, we don't even care about this displacement, so there's no point of doing it. My velocity, my final velocity, which is 0, as I discussed, my acceleration, which is minus g, and my time, which I'm just going to call t, right? So let's find exactly how long it takes for the ball to go from here to here, right? So using my Suvat equations, I can just get that t is equal to, well, just use the one which is v squared, not even this one. We use the equation that says that v is equal to u plus at. So we get that u sine theta minus gt is equal to 0, which implies that t is equal to u sine theta over g. So again, this is kind of useful, like, for the reason because I need 2 pieces of information with my Suvat equation, right? I need some initial conditions and I need some final conditions. And by picking this point in the middle, which by symmetry is going to have a velocity of 0, I can find the second piece of information that the question is not telling me. Good. So I have the time it takes for it to go from here to here. But the time that it's going to take to transverse across the whole direction, again, because of symmetry, is going to be 2 times that time. So total travel time will be equal to 2t, which is just 2u sine theta over g. Good. So now let's kind of consider the horizontal motion, which is always the easier one. The horizontal motion. There we go. And in that case, we know that t is just equal to the distance traveled, which in this case is r, over the speed, which in this case is u cos theta. Again, I'm getting u cos theta and u sine theta by resolving my initial velocity vertically and horizontally. Good. So again, same thing as I did in the last question. Let's compare these two expressions. And I get that r over u cos theta is equal to u sine theta over g. And once I rearrange this equation, I get that r is equal to 2u squared cos theta sine theta over g. And now, because, I clearly have some sort of maximization problem, let's kind of make our life really easy and use a really common kind of formula that we use in physics, that 2 cos theta sine theta is equal to sine 2 theta. Again, just a trigonometric identity that you have probably seen in school, but if you haven't, it's kind of good to know. So we get my final equation is that r is equal to u squared sine 2 theta over g. And in this question, the initial velocity is fixed, the initial speed is fixed, and obviously gravity is fixed. So to find the maximum range, what I have to do is I have to differentiate my expression with respect to theta. So at the maximum point, I get dr over d theta is equal to 0, which implies that u squared cos 2 theta over g is equal to 0, which implies that cos 2 theta is equal to 0. And once you solve this equation, we get that 2 theta is equal to 90 degrees. So theta is equal to 45 degrees. Again, let me just kind of maybe draw a cos graph between 0 and 360. So remember that my angle is clearly going to be, my 2 theta is clearly going to be between 0 and 90 degrees, right? There's no other way because I've got a fixed direction of the cannon, right? Which means that I want the solution of cos theta of equal to 0 between this kind of range here, and the only solution here is just 2 theta is equal to sorry, I drew this wrong. This is clearly not 90. This is 180. This is going to be 90. Yeah, sorry, I meant that theta is between 0 and 90 degrees, which means that 2 theta is between 0 and 180 degrees. So from my kind of plot of the cos graph, you can see that the only solution within that range of cos 2 theta is equal to 0 is going to be that theta is equal to 45 degrees. Good. So that's the first part of the question. Let's kind of look at the second. Let's look at the second part of the question, which says that show that if the cannon is at the top of a hill with an incline angle of phi, then the range equation can now be written as, so this is the goal, that r is equal to u squared over g sine 2 theta plus tan phi 1 plus cos 2 theta. So obviously, clearly, that's a little bit difficult. Right, so let's draw the situation out. So once again, we have a hill, then we have our cannon, which again, I guess it's kind of difficult here to know if it means that theta is with respect to the horizontal or, the hill. But I guess if you assumed it the other way, then you'd get a wrong answer. So I guess that's one way to consider it. But there's my theta. And again, we're just going to call this our v. And then we have a phi like so. And the total range is just going to be this horizontal distance. So clearly another Suvat equation, but it's going to be a little bit more painful this time. So what was I going to say? Yeah, so sorry, I'm just kind of making sure that I understand what's going on. So as before, we can still invoke symmetry, even though it might not seem like it. The moment when the projectile is at its highest point is still exactly halfway of the journey from being fired to landing. And that's basically, I mean, this time it's not going to be exactly in the middle, right? But the point is that, and again, it's kind of more difficult to explain. It's just kind of something that for now, I'm just going to have to make you guys trust me. But yeah, by symmetry, that halfway point of the whole motion is going to be a point where the vertical velocity is equal to 0. And that's something by the fact that, this is the same situation as before. It's just rotated by an angle, which, we're not changing much. It's still a parabola. It's just a bit of a twisted parabola, right? again, and maybe I'm not too convincing, but again, for the purpose of time, just kind of take that as a given. Good. Right, so let's just kind of do everything that we had before, and then consider these kind of 2 points, or our Suvard equations. So we've got the point here where the vertical velocity is equal to 0, as I mentioned before, because by symmetry, that's the point halfway through. And then we can well, we don't need the vertical displacement, but we do need the initial velocity, which is u sine theta. The final velocity is 0, again, because we're just considering this kind of halfway point. The acceleration is minus g and the time is t. So same equation as before, we get that u sine theta minus gt is equal to 0, which implies that t is equal to u sine theta over g. So the total time, which I guess I would call t, big T this time, just to make it a little bit more explicit. So total time for motion is t is equal to 2t, which is equal to 2u sine theta over g. Good, right. So, and I'm just kind of making sure that I understood everything. Okay, yes, good. So, yeah, anyway, so let's now do the I'm just kind of I think I just did everything wrong because I don't think you can assume symmetry. I just realized yeah, I was reading the solutions. Okay, I clearly have it's been a long day. You obviously can't assume symmetry because there's no symmetry. I was reading the solutions to part A while I was doing part B. So clearly I was just copying out everything that happened before. And then I got to the end and it was the same answer. Sorry, guys. Let me just kind of write this out again. Right. So the diagram was right. Sorry. There we go. The diagram was correct. Yeah, anyways. So let me just kind of figure this out again. Right. So so this is the diagram, right? And we can still focus on the vertical direction, right? In this time, however, what we're going to do is we're going to focus on what was I going to say? Oh, yeah, focus on what we know, right? So the vertical direction, what is our displacement going to be? Well, our displacement is, if this is r, just by using trigonometry, again, write down my vertical variables. Again, this was so silly, like clearly there's no symmetry here. I guess that's another lesson to learn, to kind of know what you're reading instead of just regurgitating everything. Right. So a vertical displacement, again, this is upwards, this is down, is going to be minus r tan phi. Again, that's just you can just get that from trigonometry. And then my initial velocity, and same as before, is u sine theta. I don't know anything about my final velocity, and I know that this is minus g, and I know that this is time. But I'm obviously not really going to care about the time. So, well, I am going to care about the time. I'm going to call this t. So I can just use my formula from Suvard, that s is equal to u y t plus a half a t squared, and substitute all my variables in to get that minus r tan phi is equal to u sine theta t minus g over 2t squared. So I can just rearrange this. So I get a half gt squared minus u sine theta t minus r tan phi, which is equal to 0. Good. So then you solve this quadratic formula, which is obviously extremely ugly, and you get t is equal to u sine theta plus minus the square root of u squared sine squared theta plus 2g r tan phi over g. And that's kind of what we got from the vertical motion. So just to quickly sum up, that the velocity clearly is not 0 at the maximum point. And I don't know what I was thinking, but clearly I'm losing it, right? But the point here is I need 2 points where I know enough variables, right? So obviously the initial point and the final point is what I'm taking here, because again, there's no symmetry here, so I can't use this kind of easy trick that I used in the previous question. So instead, I kind of use this final point, and that's why I'm going to get a really ugly equation for my time. Good. Now let's kind of focus on the x direction, which is really easy. And I get that the horizontal displacement, well, this is always easy. I get that r is equal to the horizontal speed times the time, which is u cos theta times the time, which is just this kind of big, horrible expression. So what was I going to say? So now at this point, it just becomes a really, really, really horrible, a really completely horrible algebraic problem where you have like, this is u, and then, I mean, I'm not going to bother writing this whole equation here. But essentially, you just have, you know, this terrible, terrible problem. And what we're going to do is we're going to use the positive square root because time is positive. And there are two solutions to this. And you can see that because this is always a positive factor, the negative solution, the one with the negative sign, will always be negative. That's why I'm choosing the positive sign because time is positive. So then, yeah, so basically now I have this whole expression for r. So r is equal to u cos theta, and then we have u sine theta plus the square root of u squared sine squared theta plus 2g r tan phi over g. And then finally, the question tells us what was asking. It was asking that show if the canon, then the range equation can now be written as this. Yeah, okay, good. So so then basically what you have to do is now you just have to kind of like, this is horrible, right? You basically have to expand this whole expression by kind of taking everything to the left-hand side and squaring it. So I get, I'll just kind of put the immediate steps here. So I get rg cos theta minus u sine theta squared is equal to u squared sine squared theta plus 2g r tan phi. Right, and then what you do is you expand this bracket and you get a quadratic equation in R. So I don't know what I was thinking by the symmetry, right? Because clearly this is a nightmare, right? You get an absolutely terrible expression in R. It's a quadratic formula, which you then have to solve, right? What was I gonna say? Yes, so so the equation looks like, well, it's not a quadratic formula actually because stuff cancels out, but it's still but it is a quadratic formula by far. Still, but stuff cancels out, so it's not quadratic because r is clearly not equal to 0. U squared cos squared phi theta. So basically you divide both sides by r, you solve this equation, and you get the final expression that r is equal to u squared over g sine 2 theta plus tan phi 1 plus cos 2 theta. Anyway, so this equation just uses suvat, right? Most of this is just algebraic errors and algebraic manipulations, right? So the final part of the question, and I promise for the third question, I won't make a mistake. Determine the relationship between theta and phi that maximizes the range. So basically, what we need to do is, well, the thing is that phi is something that can be fixed, right? Is we just want a relationship between theta and phi. Like, the point is that let's just kind of differentiate the equation with respect to theta. Let's say that dr over d theta is equal to 0. So we're just going to basically fix phi, right? And, we'll get some expression because, well, phi theta is the kind of only thing that we can maneuver. Again, a kind of more, what was I going to say? Yeah, so that's essentially what we're doing because we want a relation between theta and phi is just something that's fixed by the problem, right? Right, so basically differentiate this entire equation above with respect to theta and set it equal to 0. So we get that dr over d theta is equal to u squared over g 2 cos 2 theta minus 2 tan phi sine 2 theta, which is equal to 0. And then you basically solve this equation and you finally get that, well, tan 2 theta is equal to cot phi. And then you have to use another identity, which is the fact that cot phi is equal to tan pi over 2 minus phi. And that's kind of something that you can use, that you can derive by the definition of cot. Remember that cot is equal to 1. So cot theta is equal to 1 over tan theta. So I plug that in and I basically get that tan 2 theta is equal to tan pi over 2 minus phi. And then I get that 2 theta is equal to pi over 2 minus phi. Right, so this is clearly, anyway, this is the question. Obviously it's just a nightmare, algebraic nightmare. I'll answer any questions that you have in the chat. Apologies for making a mistake at the start, but obviously it's been a long day, guys, but I won't make a mistake the next question.
Genuinely, Aggie, I think you are showing us exactly how you go about problem solving, which is that sometimes it doesn't always go exactly the way you want it to go. Sometimes there is a bit of back and forth. And this is how we do it. And this is why we have you present it before we just send the solutions, because this is how it's going to be for these people when they're students with us, when they're students studying Oxford. anywhere, and in the pad itself. So please, you are doing an amazing job. I'll let you head over to the answers, which means we are now back with our lovely Roxanne. Thank you so much for answering all of your questions about trusses and gravitational forces and resolving. And I think we are over to you for question 4.
All right, can you hear me?
Yep, all good.
Okay, so for question 4, so for the first part of the question, so basically, the question is saying that as the zookeeper is here, let's say this is the ground, and then the monkey is up on a tree, and then if the zookeeper is trying to like aim at the monkey, let's say if he shoots aiming at the monkey, the dot will, because of gravity, will fall, right? And so for the first part of the question, if the zookeeper wants to hit the monkey, then actually he has to aim higher because of gravity, because like, yeah. So he should aim higher so that he could hit the monkey. And then for part B, so now the monkey is letting go. Yeah, the monkey is also falling. So let me draw a diagram again. So this is the zookeeper, and then this is the monkey. And let's say at t equals 0, they are here. And let's say maybe this is time equals 0, and for time equals t, because the monkey and the dot fall at the same rate due to gravity. And so you can think like maybe at time t, the monkey has fall like this distance, and originally the dot is aimed at the monkey, but the dot also falls at the same rate as the monkey, and so they will meet eventually at a point below the monkey. By intuition, that may not make sense, but maybe we can try to verify using mathematics. So let me draw a new diagram. So let's say originally the monkey is here and the zookeeper is here, and then I label the horizontal distance between them as x. X means vertical, and then for this I label it as h. And then at the point where they meet after t seconds, I label, the distance from the ground, I label it as sy. And so by trigonometry, tan theta, this angle, the angle of the dot above the ground, is defined as theta. Yeah, so tan theta equals h over sx. And so now we have to solve out equations. So let's now consider the horizontal motion of the dot. So because horizontally there isn't any acceleration, so sx equals uxt, where the initial velocity of the dot is u, and then the horizontal component is ux, and then the vertical component is ui. And so this is theta. So we know that ux is u cos theta. And so by rearranging, we get that t equals sx over u cos theta. Okay, so this is obviously not the answer, because we also have to consider the vertical motion of the monkey and also the vertical motion of the dot. So maybe let's start with the monkey. Sorry, the vertical motion of the monkey. Okay, so the monkey has traveled this much distance. So if I define vertical to be positive, and yeah, the downward motion to be positive. And so the displacement is h minus sy equals 1/2 ay t squared. And so if we substitute t equals sx over u cos theta, which is this one, the one that we just found previously, into this equation, I name it as equation 1. And after some rearranging, we will get sy equals h minus g sx squared over 2u squared cos squared theta. Yeah, so ay is g. Ay is the acceleration due to gravity. And so we get this expression. And then let's consider the vertical motion of the dot. And for this one, sy for the dot for the vertical motion of the dot, so it travels like this distance. Let me use the laser pen. So because the dot, it travels outward, so this is the displacement. So sy equals the original Seurat equation is s equals ut plus 1/2 at squared, right? So I construct this equation based on this. Yeah. And so sy equals uyt plus 1/2 ayt squared. And then ay now is minus g. In this case, I consider upward to be positive and downward to be negative, but it doesn't really matter. Like as long as you have to be consistent, but yeah. And so uy is u sine theta. So uy is the vertical velocity of the dot. This is u sine theta. U sine theta times t, and then plus should be minus g over 2t squared. So I label this as equation 2. And then again, I try to substitute t equals sx over u cos theta. This is actually found previously here. I sub this into equation 2. So after rearranging, we found that sy equals sx tan theta minus g sx squared over 2u squared cos squared theta. So this is equation 3. And then lastly, because we want to try to remember we found that tangent theta equals h over sx, and so the aim is to actually make this expression the same as this one. Then we can prove that they actually meet somewhere below the monkey. And so if you try to compare this expression with this expression, you can see that for this, there's a tangent theta, but there's no tangent theta here. So you're actually trying to eliminate tangent theta. So by substituting this into this expression, you'll find that sy equals h minus g sx squared over 2u squared cos squared theta. And so now the conclusion is that for vertical, like from these methods, you found that sy equals this one. And when you consider the vertical motion of the dot, you found that sy equals this, this expression. And so they are the same, they're consistent. So that means that the dot and the monkey will meet at a distance sy above the ground, where sy can be found by this. Yeah. And this is the answer to this question. Yeah.
Lovely. Thank you so much. And I think pretty much perfect timing because Aggie is just finishing the final written answers and I can buy her a minute to finish that as well.
Yeah, sorry.
No. Thank you so much. It's lovely to see. And I think this gives us a really good flexibility as well. I also like that a few people have asked quietly in the Q&A what app you guys are using. So I know, Aggie, you said you were using GoodNotes. Roxanne, what are you using to present your notes? And we can just let these guys know what we're using.
I'm using an app called Cooler Notes. Yeah, Cooler Note.
There you are, guys.
It's free.
Amazing. Thank you so much.
Let me just share my screen again.
Perfect. I bought you exactly as much time as you needed, Aggie. Winning.
Yes, thank you.
If
Okay,
anyone
good.
has any questions about the monkey problem that Roxanne was doing, pop them over in the Q&A and she can answer them while Aggie is presenting our next question. See you in a minute.
Good. Okay, good. So the question, let me just, because I just had it and then I closed it down. Okay, right. So the question starts with, we're going to be looking at motion diagrams. It has 3 parts again. So for the following scenarios, sketch the motion time graphs, displacement time, velocity time, and acceleration time. So this is kind of like, I think, well, back in my day when I was doing the PAT, I would have thought that this would kind of come up a lot in multiple choice questions. Oh, I guess the whole PAT is multiple choice now, so it can only come up as a multiple choice question. But anyways, without further ado, let's look at the first part. So the first question asks about a ball which is thrown up in the air and then caught at the same height. Only sketch it from the instant the ball leaves the hand to the instant it touches the hand again. Ignore air resistance. So if we ignore the air resistance, as we always do in physics, then the ball's weight is the only force which is acting on the ball. So we know that the acceleration on the ball is just simply going to be minus g. And again, I'm going to say that this is positive and this is negative, right? Well, that's kind of the only thing. So we just have a, normal Suvat motion, right? So kind of let's start with the, I kind of always start with the acceleration graph, because, well, that's kind of the easiest one to figure out. So we have our acceleration, and like I said before, what's going to happen is, well, I don't know, to be consistent, right? Let's be consistent. So we have the acceleration here, and we have time here. My acceleration is always going to be constant and negative at minus g, right? All good, all fine. And the next question, the velocity time graph. Well, the velocity time graph, well, we know from constant acceleration, from the constant acceleration motion, we know that the velocity is equal to u plus at. So again, this means that our graph is just going to be a straight line graph with an intersection at the initial velocity. And remember, because my acceleration is negative, this means that my gradient is going to be negative, like so. And finally, my displacement time graph, again, because this is all just projectile motion, you should be able to kind of recall these graphs very easily anyways. What's going to happen now is, again, recall the formula that I had before, that S is equal to ut plus a half at squared. You can see that we're going to have a parabola. And let's just kind of say, oh, it says, yeah, let's just kind of, for simplicity, let's just call the initial height that it starts at h. So we have the ball goes all the way up the top, it stops. This is the vertical distance, obviously not the horizontal distance. Goes all the way to the top, it stops, and then it falls back down and is caught at the same height. So that's kind of basically, that's a bit more, that's kind of, a nice start to the first question. Good, right. So the next question says, part B, a train travels from Birmingham to Oxford, stopping only at Banbury on the road. I wish. You may assume the journey is in a straight line, and it only takes a few minutes of constant acceleration, deceleration to get to its top speed / come to a stop. Okay, right. So let's just kind of remind ourselves what the difference between acceleration and deceleration is, right? So remember, acceleration, just for this type of time being, we're going to say that our acceleration is something that's positive and our deceleration is just a negative acceleration, right? So let me write it down. This is a really key fact, that deceleration is simply negative acceleration. Again, let's just start with the acceleration graph because I think that's kind of the easiest, right? So we have the train and we're going to basically consider, you know, it's on a journey, right? So it's you know, let's say that it's stopping here, right? It's stopping. And then suddenly the train accelerates. And then the question tells us that we can say that it's very short constant acceleration, right? So it accelerates and then, you know, at this point it's chewing at its speed, right? And then it's going to stop. So at this point, it's going to have a negative acceleration, also known as a deceleration, which means that, you know, we're just going to have the same graph, but turned upside down. So again, I'm just going to say that this is positive and this is negative, and this is kind of my train going in this direction, right? So again, sort of makes sense. It's again, just the important part was the assumption in the question, which stated that the acceleration is constant and short. Good. So the velocity graph. Now, again, well, let's kind of fill in the blanks. We know that here, so let's kind of make everything correspond. We know that here it's going to travel at a constant velocity, right? Because again, that's kind of what the question tells us. It tells us that between these accelerations and decelerations, it travels at a constant velocity. We know that here it's going to have a zero velocity because, you know, I just said it starts from rest. And here, because it comes to a stop, it's going to have a zero velocity, right? So to fill in the blanks, again, we know what constant acceleration looks like on a graph. It's just a straight line. And because here my acceleration is positive, I'm going to have a line with a positive gradient. And here, because my acceleration is negative, I'm going to have a line with a negative gradient. And that's basically kind of it, right? There's nothing more to say about that. Good, right? Now we have a displacement time graph, which is going to look something like this. So I guess just a quick aside, on a displacement time graph, the gradient of a displacement time graph is the velocity, of course, right? So we know that here, because its displacement is, you know, at this point before it's even moved, it's just going to be zero, right? And at this point, that's to kind of correspond to this point, the displacement is going to be some, I don't know, some value that it stops at, right? So clearly we go from this displacement to this displacement, right? And what's going to happen is that when we have a constant velocity, we have to have a constant gradient in the distance time graph, right? Because in a distance time graph, the velocity is equal to the gradient of the line. And here now we have a not constant velocity, right? Here we have an increase in velocity, which means that my gradient, which again is just the gradient of a distance time graph is the velocity. It means that my gradient is going to have to be increasing, right? Because my velocity is increasing. So it's going to look something like this. I'm kind of going to redraw that in a second just to make it look a bit more joint together. And here my gradient is going to be decreasing, right? My velocity is decreasing, so my gradient is decreasing. So if I draw it, it's going to look something like this. And to kind of make it look a bit more smoother, because now I've realized what happens, it's basically going to look like, you know, a slowing down, a straight line. So a slowing down, a straight line, and then kind of round it off. I just kind of wanted to split it into three parts to illustrate how it all comes together. So that's the third graph, right? Anything. So clearly the first two are just kind of nice and simple. So next, well, actually, the second one is a bit harder. The first one is just Suvat equations. That's, you know, you should kind of be able to recall quickly. But the second one is a bit more difficult. The third one is, however, much more difficult than the second one. So a football is dropped from a great height such that it reaches terminal velocity. It bounces inelastically such that air resistance can be ignored from this point. Sketch the motion from the moment of release until it hits the ground for the second time. So I'm going to basically quickly draw a picture, right? So I have a ball, which is dropped from a great height, right? This is what it's going to be dropped from. And then the ball goes, you know, it falls down, it reaches terminal velocity. And then what's going to happen, it bounces. So it comes here, it bounces, and then it's going to, you know, do a second bounce. Again, this is all happening in one dimension. I just kind of want to make sure that the bouncing is obvious. Bounces, and then it bounces again. So why is the first bounce lower than the second bounce? It's because of this keyword inelastically, which basically means, and if some of you have done the further mechanics module and further maths, you would know that this means that kinetic energy is not conserved. So basically, when we have two balls hitting together, when we say they are hitting each other elastically, it basically means that their kinetic energy is constant. And hence, by conservation of energy, if the ball was bouncing elastically, it would reach the same height after every single bounce, right? Oh, we want it to kind of this point, right? Good. So, what was I saying? Right. So I guess we now have to actually sketch the motion. And as I was saying, let's look at the acceleration first, right? Because that's basically the most important. Well, I think in my opinion, it's the easiest to draw, but you might disagree with me, right? So this is my acceleration. So initially, right? Initially, it's going to fall and it's just going to have the usual. It's going to have the usual constant acceleration, right? However, this time we have air resistance, which means that as the ball is falling faster and faster and faster, the air resistance is going to get higher and higher and higher, which means eventually when it reaches terminal velocity, my acceleration is going to be 0. So I know here I'm going to have a zero acceleration, right? So let's just kind of join these lines together. Again, I don't really my best guess that this is what's happening in the middle, right? Because my acceleration is meant to be getting smaller and smaller and smaller, right? Again, I just kind of know that the line has to go from here to here, and you don't need to know the exact shape, right? You don't need to know the form of the air resistance, right? Anyway, so we have, okay, so the ball falls, right? So it's like this, right? Oh, actually, we don't even need to sketch that far. It's just until it reaches the second time, right? Wait, what does it say? It says, sketch the motion from the moment of release until it hits the ground for a second time. Okay, right, so yeah, like that. Right, so this is my acceleration, and then it's going to hit the ground. And as it hits the ground, right, it's going to feel a very, very large acceleration, just very, very quickly. It's going to be a very, very small period of time, right? Again, imagine that you're the ball and you hit the ground, it's going to just be a very, very quick, we call it an impulse, right? So it's going to be hit like that. And it says from that point, the question says that from that point, we can ignore air resistance, right? Which means that from that point on is just the kind of regular graph that we had before with the gravity equal to minus g, right? Good. Again, this is kind of, remember that the question tells us that from this point on, we can ignore air resistance. So we can, recall our result from part A. Good. So we have our acceleration graph. And now again, because of everything I've mentioned before, how, well, the gradient of a velocity time graph is the acceleration, and the gradient of a distance time graph is the velocity, I can sketch the other graphs quite easy, right? Because I just have to compute the gradient of all of these graphs, right? So I have my acceleration, so I have my velocity, and I have my t. And again, this up is positive and down is negative. So my velocity, as I said before, my velocity is going to be increasing and increasing and increasing and increasing until it reaches the terminal velocity. At that point, it's just, constant. It's just the terminal velocity. Then what's going to happen is going to hit the ground, is going to get a really high acceleration. So it's going to be an almost straight line because the gradient is always going to be very, very, very large. And then at that point now it's, now it bounced. We can ignore air resistance. So we're back to the usual Suvat equation. So we just have the answer from the previous, from part A, right? Again, because we know that before. Right, and finally the displacement time graph. Again, what I'm going to just kind of sketch is the fact that, well, my velocity is the gradient of my displacement time graph. I'm going to start at some height, and the displacement time graph is kind of the easiest one to draw because it's literally going to look like a bouncing ball. I'm going to have some sort of kind of, remember that the velocity is going to be my velocity is going to be the velocity is just decreasing here, sorry, increasing here. Well, no, the velocity is decreasing, right? Because the velocity is getting more and more negative. So I'm getting a more and more negative gradient. And eventually I have a constant velocity here. At that point, I hit the ground because this is, remember that this is the terminal velocity section, which I just sketched above. And then what's going to happen is I'm going to hit the ground, which is, well, not going to go past the ground. And then I just have the regular Suvat equation that I had before, which is just a parabola until I hit the ground once more. Anyways, so that's the question. If anyone has any questions, I will answer them in the chat now.
Yeah, I think you've got a couple about sort of midpoints and a bit about how you sorted out your shape. So all good. Lovely. We are doing brilliantly on time. So over to you, Roxanne, for our second last problem, problem number 6. And then we'll return for the final resistor cube to Aggie. And then we will hit our final Q&A session for all of the general questions. Over to you.
Yeah, so for this question, it might seem to be a bit of a nightmare, but if you do it like step by step, then it will be very easy. Trust me. Okay, so before doing this question, we have to know that for like series circuit, the equivalent resistance is equal to R1 plus R2 plus like the rest of them. And then for a parallel circuit, the equivalent resistance is like 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus blah, blah, blah. Okay, so I will use green for series and then yellow for parallel. So for resistance in series, we can see that they are in series, and then these three, they are also in series, right? And then for this like weird rectangle square shapes, they can actually be simplified into like this configuration, because like the wires, they are connected like in like a mass, but then they're just equivalent to this configuration, just 2 wires like here and here. And so let me draw the equivalent circuit. So I will use this symbol to represent resistor because they're easier to draw. And so now we get 20. I'm not gonna include the unit because like it's a bit annoying, but you have to know that like when you answer the question, you have to include a unit. So this is 20 ohm. This is actually these two. And then I'm going to quickly draw the equivalent circuit. So this is 20, and then it takes a bit of time. Okay. So I'm keeping everything the same, except the 2 series connection that I've just mentioned. Okay, so I guess I didn't miss any one. All right, and so now for this circuit, this is a simplified one, and we can see that these 2 resistors, they're in parallel. Yeah, and we might like we can construct another simpler circuit, and also for here, this one we can actually simplify it a bit, and I will show you how I simplify it. So first of all, let me redraw this circuit. So this is this one. They're equivalent, and okay, I'll have to redraw it again. For this, okay. We can draw it in this way, so it's easier to interpret. I didn't change anything. I mean, I just like for this configuration, I just make this as this. Like, but they're actually the same because here the potential is the same. The potential here there is the same, and so for here the potential is all the same. So basically, I redrew it in a much cleaner way, and then here now you can see that these 2 are in parallel, right? And also these 2, and the 15 ohm and the 10 ohm resistors, they are in series. Yeah, the green one, they're in series, and the yellow one, they're in parallel. And so we can construct another equivalent circuit, simpler one. So this is 25. By the way, I skipped all the calculations because I assume that you can do it on your own. Yeah, and you can also use the calculator or like mental calculation. Yeah, and in real PAT, there's an inbuilt calculator, and yeah. So, okay, I didn't miss anything. Yeah, so this is the equivalent circuit. And then, sorry, there's always an advertisement asking me to pay. Yeah. So here you can see they're in series. Yeah, so I'm gonna draw another equivalent circuit. Okay. And now this seems a little bit annoying, right? But if we try to consider the connecting point, because this wire, they are connected here and here. So we can actually move this 100 ohm resistor to here. Well, because oops, sorry. Because the connect, oh, sorry, wait a sec. Yeah, because the wire is still connected at these 2 points, and so they're identical. And so by this point, I think things are much easier, because these two, they are obviously in parallel, and then I'm gonna draw it. So the equivalent resistance is 20, and then here, obviously these two, they're in series, and then if you combine these two, then this configuration and this 4 ohm resistor, they're in parallel, and then this configuration and this resistor, they're in series. So at last, well, let me draw it out again. So you get something like that. And lastly, the numerical answer that you found should be 31.5 ohm. Yeah, so basically you just have to like turn this very difficult configuration into like simpler configuration by just spotting out the resistors which are in series or in parallel. Yeah, so I think that's all.
Great, thank you so much. You've got 2 questions, and Aggie, perfect timing. It is over to you for our final and I believe second resistor question, even though it's the final question of today.
Yes, so let me just share my screen. Right, so this is a bit, I know you can't see it, it's loaded, but this is a slightly difficult.
That's you.
Oh, good. This is a slightly more difficult problem. It's a very common problem. Like it's like you probably will see this many times wherever you go to study physics. So once you know how to do it, it's very common. And I think, in my opinion, it's quite a difficult question to get your mind around. But it has a lot of important concepts. So before we even start this question, I just really quickly wanted to mention something in circuits, right? So with circuits, when I have 2 points like this, let's just consider 2 points. And if I have 2 points which are at the same potential, right? If I put a wire between them, because they're at the same potential, like here and here, there's not going to be a current flowing across it, because in the same way that I'm not going to have a river flow if I don't have like a bank for it to flow down. If there's no potential difference between 2 points, there's going to be no current flowing through it. So I can just simply put a wire between these 2 points. Like nothing's going to happen. I'm not changing anything. That's just kind of a key idea that I wanted to highlight during the question, right? So essentially, the question has a cube, right? The question has a cube like so, and each side of the cube has a resistor. I'm just, to kind of keep it nice and easy, I'm gonna kind of not, I'm not gonna draw that out. I'm not gonna draw every single resistor on the cube. So it looks something like this. And I have point A, and then I have all these points inside this resistor. Where's the other one? So One wire is connected to vertex A and the other is probed around the other vertices in turn. Right, so yeah, as I was saying, let's just kind of, so this is point A, right? And just again, I'm just copying down this diagram. This is going to be point D. Then we have, what do we have here? We have B, H, and F. So we have B, H. Oh, I drew it in a different, okay, B, H, and F. And then I have for the final points, I have E, G, and C. So I have E, G, and C. Okay, so I have all my points, right? And again, kind of a key problem that you have to consider is that when I'm putting the wire here, again, lots of symmetry, right? That if I'm looking down, like if I was looking down at this resistor here, and I kind of, this is a question because it's so common, you can find many, many explanations on YouTube if what I'm saying is not a very good, explanation or a very good visualization given the time limit. There's many ways that you can do it. There's many different ways to think about it, but I'll just go through kind of one of the ways, right? So by using symmetry, I can tell you that this point, and this point are all at the same potential, right? And again, you can sort of think about it, right? If I was looking at it, it was kind of dangling down, right? Like I can rotate the cube, right? If I rotate the cube, it's easier to visualize for some people than others. If I were to rotate the cube, right, so that H goes to B and F goes to H, I would get the exact same cube, right? It would all be identical. So that's why my B, H, and F have all the same potential, right? And so do my E, C, and G. Because again, if I were to rotate my cube while I was at A, so that G goes to C and E goes to G, I would get back with the exact same cube. And then I have my point G, which doesn't have anything special about it. So again, if I kind of maybe draw it a bit kind of more 3D like so, like if it was hanging, if you think about it, like if it was hanging like a decoration, right, it would look something like this. So I guess maybe that's slightly easier to visualize why you have all these symmetries. Maybe that's just made it more confusing. Okay, well, that's a terrible drawing of a cube. But the point is that you have these 3 points of equal potential, which basically means that I can connect all of them by this wire, right? I can connect all of them by this wire. And what happens is if you consider the case where I make, because there's no current flowing between these wires, right? And let's just kind of make these wires smaller and 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 smaller. Well, now I can kind of redraw this circuit, right? So I'm going to make the wires so small so that B, H, and F are the same point because they're at the same potential, right? I'm not doing anything. I'm not changing anything to the circuit by adding these wires and making them smaller. Because it's the exact same thing. I can make my wires as long as short as I want because, again, this is ideal. So the length of my wires is not going to matter. So let's kind of draw what we get. So we're going to have point A here. And then from point A, we are going to have the point, the point B, H, and F. So between point A and this green point, we are going to have 3 resistors, right? We have this resistor, and this resistor. So let's draw it out. And they're all in parallel, right? You can sort of see it because when B and H become the same point, this touches this, and we have 2 resistors in parallel. So this goes like so. So 1, 2, and 3. Good. So again, same situation for D. So let me kind of draw this out. If I have my C, E, and G point, exactly same discussion as I had for A. I'm just going to have my 3 resistors like this. I'm going to have 1, 2, and 3. And then I have my, just my wire here. And this is point D. And then I have, what is it? It's C, G, and E. Now what's happening in this final wire, I need to find all the connections between, my green point and my blue point. So I have 1 resistor here. I have 1 resistor here. I have another resistor here, another resistor. Again, just to kind of just have 1 here, 1 here, 1 here. Then I have 1 here, 1 here, and then I have, there's basically, it's kind of hard to visualize from my drawing, but the point is that there are 6 resistors in parallel connected between these points. So I have 1, 2, 3, 4, 5, and 6. So the key to this problem is to basically use symmetry so that you can connect all the wires with 0 potential difference. And at that point, you can sort of manipulate the cube. Again, some people find it really easy to kind of do these maneuverings of this cube in your head. But if it's something that you struggle with, then I, suggest that you get a piece of string and see if you can kind of resemble this. Because the thing is, as long as I'm not changing any connections with a potential difference, everything's exactly the same. So now I have the setup, right? And the question tells me, I have this cube. One Y is connected to vertex A, and the other one is moved around the other vertices. Determine the vertex reading in its position. Okay, well, let's kind of simplify this, right? Just kind of using the fact that in parallel, so remember, in parallel, if I have two resistors in parallel, R1 and R2, the total resistance is given by 1 over RT is equal to 1 over R1 plus 1 over R2. So I'm just going to basically apply this to all of my resistors here, and I get that this resistor, the one between A and B, H, and F, can be replaced by R is equal to 1 over 3. The one in the middle is equal to R over 6. And the one here is equal to R over 3 again. And this is my point D. And this is my point CGE. Again, just to kind of demonstrate, here I would have 1 over RT is equal to 1 over R plus 1 over R plus 1 over R. So RT is simply equal to R over 3, right? And same with all the kind of other parts. Good. So now the question becomes really easy because, well, if I plug the wire in at, if I plug my wire in between A and B and H, clearly my resistance is going to be R over 3. So B, H, and F. My resistance is going to be R over 3. If, however, I plug in my wire between A and CGE, well, my resistance is going to be equal to R over 3 plus R over 6, because now they're just in series, which is equal to R over 2. And finally, if I plugged it between A and D, well, then my all resistance, this is just kind of, I should probably have connected it. This is I probably should have just kind of, put the connection here, right? But if I connected it between D, well, again, just add all these resistances here, and I get R over 3 plus R over 6 plus R over 3, which is equal to 5R over 6. Again, this is a really hard problem, but it's a really, really common problem, which kind of uses a lot of these skills, like connecting these wires. So it's connecting these wires between between points of zero resistance. But yeah, that's kind of my question, and I guess I'll pass on to Helena now to answer some of your questions.
Hi everyone. Oh, I think Kat dropped out for a bit, so I'll just say a quick hello. Kat's back. Yay, with no sound. Sounds off.
That's okay. I just haven't pressed mute. My internet's completely died, and I was terrified that everything would have stopped. I am so relieved to see that the webinar is still running.
Yes, good. Well, I literally just started talking for about 10 seconds because I realized, oh, Kat's disappeared. Do you want to sort of introduce what the next
I was just about to introduce you. So I assume the wonderful Aggie has finished presenting her solutions, as is her wont. So that brings us to the end of our preparing for the PAT course for this year, which is very exciting. And now we have got up to 30 minutes where you can ask all of your questions, including to the lovely Helena. So feel free to continue introducing yourself.
Yeah, so I was literally just about to say, hello, I'm Helena. You might recognize me if you've been watching the PAT Problems videos. I am the other presenter alongside Kat, who's been going through those solutions. And the reason why I've been doing that with Kat is because I am basically her equivalent in the material science department. So material science, as I'm sure you're aware by now, is another one of the departments that asks for you to sit the PAT if you're applying for our subject. And that is why I'm here today. If you have any questions about how we use the PAT, any advice, that's what this last sort of 25 minutes is for, I believe, Kat, isn't it? So please do start typing questions because the departments do use the PAT in slightly different ways. So I can talk a little bit about that if that's of interest to people. I think things are still slightly up in the air with it changing its format slightly, isn't it, Kat? It's a kind of uncharted territory for us as well as for you with these multiple choice questions, isn't it? So,
well, I guess that's a really good point to say. So I don't know about you, Helena, but I've been getting a lot of questions about how are we going to make this fair for everyone this year. And I think what's really important is that we never compare between year groups.
No.
We only ever compare each year group. So all of you who sit the PAT this year, we will look at all of your results and we'll find out how well you did with the PAT, how you found the multiple choice. And that's what we're going to be using as our basis. We're not going to be comparing to previous years.
Yeah, that's a fantastic point. So if everybody struggles with the multiple choice questions, we will see that everybody has struggled and we will be able to scale things accordingly, just like we would, or you would with your A-level exams as well. You know, it's just you as a group who are applying this year. Don't worry about the examiner reports for previous years. You know, it's all good practice still to do the past papers, but don't worry about any of that. Just focus on you as a group this year. So don't worry about what's gone before. Just do your own practice and focus on doing the best that you can do.
Absolutely. But we have got a few questions about how the PAT is used in materials science. So while you decide exactly what you would like to say about that, I'm going to take a couple of the very practical questions. So I've got a few people who have asked things like, in the PAT exam, am I going to be able to see which questions I've flagged and questions that you've done because they weren't able to do it? In webinar 5, we had an hour and a half just on the practicalities of that paper, and I took you through suggested exam techniques for those ideas. So I would highly recommend going back through webinar 5, where it shows you how to get to a final screen where you can see flagged, not done, coming back to. So have a look back through webinar 5, sorry. And Helena, if I take off that one, why don't you tell us a little bit about the PAT in materials science?
Yes, so hello to people who are interested in material science. We love to have you here. Yes, so because material science is a much smaller course with much fewer applicants, we don't need to be possibly quite as strict in our use of the PAT as, say, physics or engineering. We actually can look at everybody's application and look at every piece of information within that. So for us, the PAT is very much a piece of information that we add to your UCAS application, to things like your predicted grades, having a look at your personal statement. So what I was doing just a minute ago was actually pulling up our feedback leaflet from the last admission cycle, just in case there's anything interesting that I could specifically mention there. Worth saying that we do publish each year a leaflet on our website with very detailed information about how we use every single piece of your application. It shows you the statistics for the PAT marks for people who were given interviews as well as given offers. So you can sort of see the spread there and you can see how that might vary to somewhere like physics. I believe physics, you also publish that data. Am I correct in saying that? Is that in your exam?
Absolutely. So we publish an admissions report every year, which has all of the information, all of the formula that we've used, and gives you a really good idea.
Yes. So we do use an algorithm. It's quite a simple one. I've just got it up here. And that algorithm weights the UCAS. So we grade your UCAS applications, and that is weighted more strongly than the PAT score for us. So it really is just an additional piece of information. For us, it's not like the main piece of information. It's not a pass or fail situation with the PAT. It's added as sort of an extra piece of information in that sense. I will pop a link in the chat actually I can do that to everybody. I have permission.
Yeah, absolutely. Well, if you want to focus on that, because I know what it's like when you're attempting to write and type at the same time.
I've literally just dropped the link. So that is a direct link to our admissions feedback leaflet from the last year. So I'm not going to bore you with all the details that I was just kind of reading off there, but you can see in detail exactly how we use the PAT. What we've done in the past as well is our tutors have been able to see your physics marks and your maths marks separately. I'm not sure if that will be the case this year, given how it's being marked. I don't know how we might get those results presented. I don't know if you have any more information on that, Kat.
As far as I know, tutors will be able to see not just a score, but how that score breaks down as well.
Fabulous.
So it's one of the benefits of this is that we should be able to see all of that information. We're certainly expecting to.
Great. So that does mean that our tutors will be able to see the physics mark and the maths mark separately. So they also take into consideration, maybe you just had a really, really bad day and forgot all your physics equations, but you were really, really strong on the maths, or vice versa. So we can see that as well. It's not just an averaged out score. So that's another really useful piece of information there.
Lovely. And I've popped our equivalent admissions reports up just underneath Helena. You'll be able to see that we have a slightly higher reliance on the PAT scores, but we also do consider all those other things, just as Helena has said. So we've got a few people asking about how important the PAT score is. It's really important both for getting shortlisted, but it also helps us make part of our decision once we've interviewed you. So we'll be looking at your interview score and your PAT score. I'm going to address a really important question we've been asked as well. Got a lot of people asking, because the PAT's going to be sat at different times this year. A lot of people are really worried that it's going to be being leaked. And I think this is a really interesting one, because it's probably never occurred to everyone that the PAT has always been sat at different times, because the PAT is an international test. So we have always actually had the PAT going on at multiple times around the world. All that's different this year is that there are also different sittings within each time zone. So what we have is we have a scenario where nothing can be taken in or out of exam rooms, as we have in the past, and very secure surroundings to make sure that no cheating can take place within the exam rooms. So we have exactly the same precautions that we have always had for having the PAT being sat at different times. It probably just feels strange to you because it's probably never occurred to you that we've always had a set of time zones. And Helena's laughing because Helena and I know this well, where we'll start getting results from the first sittings coming in when Japan and New Zealand start sitting theirs, and we're with them the whole way through until the other side of that dateline sit theirs too.
Yeah, it's fascinating. It's like New Year's, isn't it?
It is, yeah. To the PAT.
Excellent. So I've just been skimming through the questions, and I can see there has been one that I assume is material science focused. So someone's asked, how are our other skills in subjects like chemistry evaluated? So that's a really, really good question for something like material science. So as you know, if you've looked into it, material science, I think, is a fantastic subject because it is quite broad. So it takes bits of physics, bits of maths, which are obviously strongly evaluated through the PAT. But there's also bits of chemistry in there, which are very important when it comes to the course. Now, you'll probably have also noticed that chemistry A level is not one of our required subjects, but it is a strong recommended subject. Yeah. Or not, you never know. Hopefully you'll realize if you've done your research into your course. But we do still evaluate chemistry knowledge. So we would expect as a baseline everybody to have good GCSE chemistry knowledge. So if you're not studying A-level chemistry, obviously we will see that, the tutors will see that on your application form because it will not show up on your UCAS. And we won't expect you to know A-level chemistry topics unless you've mentioned that you've done some self-study or something in your personal statement. But we will expect you to remember your GCSE chemistry, to use that as a bit of a foundation. And the way that we might possibly evaluate that knowledge is through the interview. So that's where that might come into play in material science. So just like physics, the interviews will be academic focused. We might also ask questions about the personal statement to pick up on a material science topic that you mentioned there to guide the discussion. That's quite common, doesn't always happen, but it is quite common. And you might also get more chemistry-based questions, more chemistry-based problem solving in your interview as well. So that's where the other subjects are evaluated more in the material science application process. So hopefully that answers that question.
Thank you so much. And I guess that kind of segues into typical question for us, which is very similar. What about further maths? So Helen and I quite often present together, and we always have pretty much the same response, which is for physics, we require physics and maths, and most people offer further maths. For Helena, she requires physics and maths, and most people offer chemistry. If you do not have further maths, that's absolutely fine. What we are looking for in physics in particular is your ability to study maths at that level. So we're looking for you to demonstrate that through your PAT, but also through your own motivation and through what we see at interview. So I know I've had a few people talking about that. What else have we got? got a few people talking about GCSEs. This is another one we get asked significantly, isn't it, Helena?
Mm.
And our answer tends to be we're not that bothered about them.
No, the way I
Seems
always
to
answer
upset people,
this.
doesn't it?
Yeah, no, the way I always answer this is your GCSEs are important because they got you onto your A-level courses, right? You will have had to achieve a certain grade in your GCSEs to be able to do physics or maths A-level. As a physical science subject at university, we do look at GCSE results. However, they're not as strongly weighted as you might think. We would expect to see good grades, so 7s, 8s, and 9s in the sciences, in the maths, possibly also English for communication skills as well, although not quite as important. But I always say if you've completely failed your, I don't know, GCSE music, completely failed it, but you did amazing in, your physics, chemistry, biology, and maths, we're probably not going to care about that low grade in music, really, at the end of the day.
Yeah, and we have a really similar stance on this, which is it's not that big a deal for us. We're much more interested in who you are as a person at the point that you're applying to us and you showing us what you're able to do now.
Mm-hmm. Yes, absolutely. We obviously realize that people can have underperformed in GCSEs, but then do fantastically in A-levels because, your work ethic kicks in or certain things resolve themselves in your personal life, which means that it's easy to focus on work. So it's those A-level predicted grades that are more of interest to us than those GCSE grades. We are also interested in any contextual information that your schools can provide about GCSE grades, about academic performance and progress, including A-levels. And we see that predominantly in the teacher reference part of your UCAS form. So that is also something that we do see and take into account as well.
Absolutely. And we've got a few people, and again, this is something that we see a lot where we start to get people asking exactly what percentage and what weighting we have for these particular things. So what percentage is going to be this? And I would say it's really not a straightforward 10% is your score, 10% is your UCAS form. We look at each application as a whole. And I know that when you're trying to write your application, you really want that answer because you want to know that you've got that 5% nailed. But the reason we can't give you that answer is because it's not that simple. So we are looking for your entire application. We want to find out about your motivation and your personal statement and your overall academic performance, but we also need to see that PAT score. So all of these questions where people now come back to us and try and phrase it a bit differently to get us to commit to a percentage. Unfortunately, there is not a straightforward percentage, but do have a look back through our admissions reports and you can get a feeling for the kind of scores that we invite to interview each year. And particularly in physics, it's always interesting to see some of those high scores on the PAT that get interviewed but then don't gain places, and scores right down at the opposite end, people with lower PAT scores who we decided to shortlist, having looked at everything else in their application, who were offered places. So do have a look through those. We've put them up for material science, we've put them up for physics. As far as I know, engineering and chemistry, you should be able to find those on their websites as well if you have a look.
Yeah, so just like Kat was saying, all that information is also available for material science. I don't know about you, I enjoy looking at the statistics. I find it really interesting. So I can see that I've had a question specifically about material science interviews. Am I right to just answer that quickly?
Yeah, please do.
So it's a good question. So are material science interviews similar to physics interviews? And hence, should I begin preparing by doing questions on Isaac physics? Or should I focus more on understanding the content in my personal statement? So that's because I mentioned that we might ask you questions about your personal statement at the start. That's a little bit of a difference to physics. I believe that's less common in physics. Is that right still?
I apologize. I was answering a question typing. Would you repeat that?
That's
to me?
okay.
And I'll get...
I was mentioning how in material science, it's quite common for us to start an interview with a question about personal statements. Is that less? Yeah, that's less common in physics.
Yeah, less common. If we're asking you anything nice, it tends to be what's your name, and then we're straight in with the academics. Some tutors do ask a quick personal question, but it's a very, very short, irrelevant part of our interview.
So what we've learned from that is material science tutors are much nicer, right?
No, they're less interested in your physics.
See the friendly rival we've got going on here. It's all good.
Our tutors are lovely, they just
Yeah.
get stuck straight in there.
Yeah. Whereas I think the thing with material science, like I mentioned before, because it is so broad, it can lend itself to a nice cross-disciplinary conversation, which still allows tutors to tease out that academic ability and knowledge and motivation through just a discussion. So it's because it's a different type of subject, I would say. But equally, you will likely be asked problem-solving questions like, here's a graph. What does it show? Let's talk about this. Here's a problem. Can you solve it on a piece of paper? Talk me through your solution. Hold it up. Show me what you've done. That sort of thing. So it's a bit of both. So I would absolutely familiarize yourself with your personal statement. Anything that you write there is open to being asked about. So please don't lie. Please don't exaggerate. If you mention a book, particularly if it's one written by one of our tutors, be prepared to talk about it potentially in detail. Obviously, they won't expect you to have the same amount of knowledge as an academic or even an undergraduate on the subject, but they would expect you to be willing to talk about it, engage in that discussion, and sort of banter a bit back and forth with the tutor to help expand your knowledge and sort of take their prompts and roll with it and see what you can come up with on your own. And the same is true for the problem-solving style questions as well. You might be presented with something, and the same is true for physics. You might be presented with something that you're not quite so familiar with, but with the physics and maths, and in our case, chemistry tools that you already have, you should be able to at least start to solve that problem. And again, talk it through with the tutor, have a bit of a back and forth, use their prompts, see how you can take those on board and build on that. So yeah, it's a bit of both for material science interviews. So practice both is what I would say.
Absolutely. I'm just working through our questions to make sure we get everything. So again, a couple of practical ones. Interview shortlistings usually go out end of November, start of December. It's a very quick turnaround from your point of view, from the point where you get an interview, an invite to interview, and then your interview. There's sometimes only a week between that. Usually it's 2 weeks, but that's because we spend a lot of time marking. So that gives us a chance to talk about the marking process. And again, we've got a few questions saying, if we're not getting our results, I'm just going to find out if I was off an interview, how do I know it was fair? So I think Helena and I can both tell you, our tutors put in hours and hours. This is an enormous part of their year. So our admissions team will have worked together to put together this test. They've worked really hard to select intelligent multiple choice answers. So it's not a case of they've chosen one and then they've put up a load of other options. They have actually sat down, decided what they think are the most likely routes students will take through these problems. Teachers in schools have also been consulted about what are the likely routes. They've selected good answers. All of our tutors are then going to get together and look through what the performance is both individually and as a whole to make this process as fair as possible. In the case where we are not able to make the kind of decisions we would like, we interview more candidates.
Yes, which is what happened for us at least last year because of the issues we had. We expanded the amount of people that we invited to interview to help compensate for that.
Yeah, so usually in physics, we interview around 2.5 people for every place. Last year, we took that up to 2.9 people per place, which doesn't sound like a huge increase, but once you actually think about it, that's almost interviewing half a person more. Everyone gets at least 2 interviews. So we will be keeping that as fair as possible. A few people asking about extenuating circumstances as well. These are things that are great to have in your teacher reference. Find out a little bit more about yourself. So that all goes into our other information category that we have about you, everything on your UCAS form. Really important to note, we always take these things into consideration with that whole application, but it's never used to reduce your offer. And nor is it used as a percentage change to PAT scores or anything like that.
Yeah, that's a very good point. The standard offer is the standard offer. Yes. I did see I've seen some questions about personal statements, which we were talking about before, so I can quickly talk a little bit about that. So I saw a second ago when I was scrolling, someone was asking about mentioning something in their personal statement that they might not have completed yet, like a research project.
Yep.
I think that's absolutely fine, and you can absolutely mention in the statement that this is ongoing. Or you can also mention, if you're asked about it in the interview, that it's not quite finished yet. I always remember a story from one of my ambassadors who's a current student in material science at the moment. He said that he mentioned it was either an EPQ or an other sort of research project in his personal statement that he hadn't quite finished or hadn't decided to finish by the time he got to interviews. He got asked about it in the interview. He just explained, oh, I haven't finished looking at that yet, but this is what I've done so far. And obviously he got in and he's now doing a PhD with us as well. So that's absolutely fine.
Amazing.
Also, would you suggest talking more about personal research or about hands-on experience? Entirely up to you, whichever shows your passion and your motivation more. That's what it boils down to in the personal statements. That's what we want to see. So however you personally can demonstrate that interest and that passion and that motivation, that's what you should write about. There's no box ticking exercise for personal statements. The more personal, the better as well.
It's another of our really tricky ones, isn't it, Helena? Where everybody wants us to be able to say,
here's a list of exactly what.
Have this.
Yeah.
And actually,
add this. No,
we look at them all.
Yeah, we do. Yeah.
So we look at everything, we take everything into consideration, and then we make our decisions. When Helena and I are lucky enough to have a range of our undergraduates, we can usually have as many takes on a personal statement as we have undergraduates with us. So Helena and I have done events where we'll have 10 undergraduates and they will tell you 10 weird and wonderful variations on the personal statement that they have. But I think we are very much reaching the end of our time. So I think we've managed to cover most of the themes. So I think really importantly, some of these questions that you guys are asking about particular things like what's the formula, what are the scores, these are all on our websites, as are all of the key dates that a few of you are asking about. So when are shortlisting coming out? When will we be sent the results? All of these are on our websites. You can look back through all of our webinars as well to find this information. And a few things that we've had come up, which feel like a really good place to start, is if you've done these webinars, if you've done all the past papers, what else can you do to prepare? So Helen, I know, is a huge fan of Isaac Physics.
Yes. I'm a huge fan of Isaac Physics. I use it in a lot of outreach events. So if you ever come to one, or if you came to one of the material science residentials, you would have seen me doing my Isaac Physics. If you came to one of the materials open days or things like that, I will always mention Isaac Physics. It's fantastic. Do as much of that as you can. If you think you've done all the questions, go back to the super challenging ones and try them again. You'll probably have forgotten how to do them. I know I usually have. Another resource that I'm a huge fan of is the British Physics Olympiad as well. Fantastic questions that are almost at undergrad level. Some of the questions that I have seen on the Year 12 BPHO papers, I swear to goodness, I've seen them on my prelims papers, which are our first year exams, or even my third year condensed matter exams. There was a crystallography, like crystal structure question I saw in that. This is a watered down question of my third year question. I remember this. I have trauma from this.
This is a lovely way for me to segue, Hannah, because my top tip is to have a look at exams from different countries set at the same level as you. Because what you're doing when you sit the PAT is you're taking knowledge that you already have, but in an exam format that you've never experienced before. For all of our students who are sitting UK A levels, we say they're UK A levels. They are not. There are at least 4 sets of curriculum in the UK. Have a look at the Scottish Advanced Higher papers. They do semiconductor physics, Helena. So for them, it will not have been as big a leap. And the British Physics Olympiad is a British Physics Olympiad.
Yes.
So English students, have a look at Advanced Hires. Any Advanced Hire students and Welsh students, have a look at the English UK papers. Look at those A-level papers, the top tier. Have a look at the IB higher level papers. Have a look at the American Advanced Placement papers. And all of this is going to give you new context in which to explore your physics and make you better prepared. And remember, as we bid you goodbye, all of this preparation is not just for us. By having submitted your UCAS form at this point, by having attended preparing for the PAT and getting all of this done, you are putting yourselves in an amazing position to be fantastic scientists. You are going to go on to amazing universities. So goodbye from me and Helena for another year. We'll be back with our videos next year.
Our YouTube stardom.
Absolutely. When we get recognized at Open Days, it's the most niche stardom we could hope for.
Do love it though. If you do recognize us and you see us, please come and say hi. I love it. Makes me feel a little bit famous.
It does. It's like tiny fame, but it makes us very happy.
Yeah.
Feel free to contact us with any questions that you have. And goodbye for now, everyone. We're going to switch off our camera as well, that any more questions come through. We'll see you very soon. Thank you so much. Goodbye. Good luck.